Okay, everybody, please take your seats. We're going to start. And for one thing, I now understand why the previous chairs were squinting. And just if any of you didn't know, that this session is being taped for being viewed later. So all the speakers be on your best behavior. So I'm Linda Burns. I'm the director of NARCAP and the co-chair of this session, along with, who are you? Bill Gutowski, I knew. I just wanted to say a word of welcome to those of you who are in the audience and to everybody who has contributed to NARCAP being the success that it is. And without further ado, Bill is now going to introduce me because I'm the first speaker.
Our first speaker this afternoon is Linda Burns, who's going to talk about, not surprisingly, the North American Regional Climate Change Assessment Program, overview of climate change results.
Thanks, Bill, for that warm welcome. Do we have a pointer, for example? Shouldn't pointer? Pointer? There in the corner of the podium. Oh, got it. Okay. Works. Okay. Did you start the clock? Is the clock running? No. It's okay now. We'll really have this down by the second talk. I'm the guinea pig here. All right. So I'm going to give you, and I've done this several years in a row, actually, an overview of the climate change results. The good news is that now we really have virtually all of them. And so I'll be presenting some sort of samples of the overview results. So first of all, a review of what the program is for those of you who could possibly not know at this point. It's the North American Regional Climate Change Assessment Program, known as NARCAP. Its major goal is several. The program explores multiple uncertainties in regional and global climate model projections. And we used 4 different global models to drive 6 different regional climate models. Another important goal is the development of multiple high-resolution, the resolution of these runs are about 50-kilometer, regional climate scenarios for use in impacts and adaptation assessments. There's also an important evaluation phase, looking at the model performance, in which our final goal is really to try to establish the credibility of the individual simulations in terms of how credible their future simulations are. There's a cast of thousands. These are the organizations involved in the program. And this was initiated about 2006 and is funded by NOAA, NSF, DOE, and the US EPA. About a 5-year program. This is kind of its extra year, shall we say. So here's the cast in more detail. Obviously, I'm not going to read out loud all of these people, but it's quite a large ensemble of people, and everybody has really worked tirelessly, I would say, to bring us to the point where we are at this moment. So here's the domain with the topography represented. So the topography is represented for 50 kilometers, the warmer colors obviously being the higher elevations. Here is the organization of the program. Phase 1, which I'm not discussing today, is this 25-year simulation using NCEP reanalysis to boundary conditions, 79 through 2004. And the overview paper for that phase was recently published in September in BAMS. The phase 2, which I'm discussing today, are the climate change simulations. There are 2 parts. I'm only going to discuss the first part of the regional climate model runs, the 50-kilometer resolutions, nested in global climate models. I'll also say a little bit, and an important part of the program is quantification of uncertainty at the regional scales. I mentioned the importance of scenario formation for the impacts community. We're saving 53, yes, count them, 53 different variables saved at 3-hour intervals. So there's a lot of data out there. So if you haven't had a chance to play with it, we encourage you to sign up. I'll say something about that at the end. We've also saved all the data that's necessary if one wanted to downscale further from the 50 kilometers. to higher resolution, 10 kilometers, for example, and a number of people have produced higher resolution simulations from the NARCAP results. So phase 2, climate change. Here is the well-worn diagram. We did only one emission scenario, a higher end one, figuring that particularly for adaptation, if you could adapt to a higher end scenario, you can probably adapt to a lower one, plus the fact that over the past 10 years, we've been actually producing greenhouse gases at a rate close to this higher end scenario. So the 4 global models, the GFDL, the Canadian, the Hadley Center Global Model, and the NCAR-CCSM, producing data for a time slice for the current 71 through 2000, 2041 to 2070. So all these models are providing boundary conditions for these 6 different regional climate models that all differ in terms of their parameterizations, their physics and dynamics. And the institutes or organizations that were running the models are indicated below. The AOGCM RCM matrix. I've spent a great part of my life waiting for this matrix to turn red. Good news for my life, it's almost complete. The red indicate the simulations have been finished. The double asterisk that the data have been loaded. And we have all of them except this last one with RSM. So that means that we have 3 sets of runs where the global model has provided boundary conditions for 3 regional models, and each regional model uses boundary conditions from 2 of the global climate models. This is a fractional balanced factorial design. I think it's the only multiple RCM, AOGCM program that actually has a statistical design about how the, what is being simulated with what. So these 3 sets are the 3 of the GCM, the CGCM, 3 of the Canadian, the CCSM, and the GFDL. So now what I'm going to do, actually I'm going to go back. I'm going to present you, so that's the overview of the program. I'm now going to present you some overarching results. The first one, I'm going to present you some results for changes in summer precipitation. And for comparison purposes, we're first going to look at what that looks like from the 17 GCMs that were used in the AR4, the CMIP3 dataset, change in summer precipitation. And this is following an agreement and significance approach developed by Claudia Tebaldi and colleagues. So this is showing, obviously, the percentage change in precipitation for the summer. Where you see the cross-hashing, that indicates that at least 50% of the models show significant changes, and that 75% of the models agree in the direction of change in precipitation. So what we see here, and what we want to focus about, is this kind of band of decrease, but for a lot of this, the decrease is relatively small, between 5 and 10, except for that significant decrease in the Northwest. These are the 4 GCMs that were used to drive the NARCAP models. Obviously, with just 4, it's not as if I'm trying to show significance. I'm just showing what these 4 are showing. The white areas are areas where there is significant change among 50% of the models, but there isn't agreement among 75. So by 75, we mean 3 out of the 4 models. So this is just to sort of orient you. The information content of the graphic itself is rather limited, of course. When we get to the 11 sets of RCMs driven by those 4 for the change in precipitation, we see something of a different pattern. We see a deepening of the change in precipitation now in this swath closer to -10 to -20. And we see this kind of little island chain, shall we say, of significance, particularly centered here in the southern Great Plains. And then we see these areas of significant increase in the northern parts of the domain. So here is a graphic of a region back here. It's sort of the Central Plains, pretty much right in there. This is just a change in temperature and change in precip plot for the 11 sets. And the point here is to show that the reason, why do we get that deepening? Well, because, for example, here is the global model result for the CCSM, and then these colored circles are the results of the RCMs driven by the CCSM. And you can see for that one, all three of them produce decreases where the CCSM was producing increases. We also see that tendency for the CGCM3 simulations. Two of them are negative. And then for the GFDL is the most negative global model, and the three regional models driven by it, one of them is even lower, but the other two are also negative. Our newest result is this one, the MM5, driven by the HAD-CM3 model, and here is where we get a contrary tendency. Here's a decrease from the global model, but an increase for the MM5, and the HAD-RM3 is kind of a wash. But ultimately, we see two nice things here. We see this strong relationship of larger temperature change with larger decreases in precipitation. And we see this general tendency for greater drying in the RCMs compared to the global models. Now, I'm going to switch to another factor here. And this is the patterns that we see between the GCMs and the RCMs. And I've shown these slides in earlier talks, but my purpose here is different. This is the change in global temperature for winter from the CCSM3. And these are the results from the three RCMs driven by the CCSM3. Obviously, the warmer colors are going up to, I think, 7 degrees centigrade, down to just 0.5. What we see here is, of course, this pattern of very large warming towards the north. All right, and you see that it's very similar in all four of them, which is something what we might expect given the large-scale nature of winter weather for the most part. Where we see a difference, it's here in the Rocky Mountains, where we have much more detailed results for the RCMs, since the temperatures are you probably have a snow albedo feedback, and I hopefully will have time to show that, but my time is running very fast, as always, and I haven't even made too many silly jokes. Okay. Summer, the point here is the pattern in the summer is really quite different. The RCMs bear very little resemblance, some resemblance, but much less resemblance to what's happening with the CCSM. And this suggests, I'm making this representative of more of an effect of the RCMs in the uncertainty or the variance of the changes in temperature. Now, one of our colleagues, Steve Sain, did a very nice analysis of variance study for these. And basically, I'm not going to go through hardly anything, really. The focus is on three sources of the variation: the AOGCMs, the RCMs, and an error or residual term. And this model postulates that the total variation in the RCM output can be decomposed into these three terms. And we perform these, or rather Steve performed these seasonally for temperature and precipitation over the Bukovsky regions that Melissa Bukovsky developed to regionalize the domain in areas of similar climate. So I'm just going to show you the ANOVA results for temperature. And the major messages, so the red bars indicate a high contribution from the GCMs, the blue high contribution from the RCMs, and white the remainder or variance term. And what we see is in the summer temperature, we see a strong dominance of the RCMs, sort of reflecting what we saw in the samples from the CCSM-driven runs. And then in the winter, we see an area of a lot of regions where the GCMs dominate, but we also have this area where the remainder term is very strong, and that can mean several different things. It can mean an area of very high variance, or it can mean a region where the GCMs and the RCMs are responding very similarly. And it's hard to separate those two factors out. I'm just going to quickly show you one slide for change in snow that a new postdoc, Rachel McCrary, is working on. And this is kind of just a nice indication of where we see in most of these models the snow retreating in the mountain areas, but you see different patterns basically based on the precipitation that's produced by these, but also the strength of the temperature regime. And we hope to be able to do a good analysis establishing the added value of the RCMs. And I'll skip that one. Quantification of uncertainty, since, does this clock now mean that I'm over time?
No, got 30, 20 seconds.
Oh.
40 seconds.
40 seconds? Don't I actually have? No, never mind. I just want to point out that we are doing a lot of work on quantification on uncertainty, particularly using performance metrics. And just to point out several different talks, Melissa Bukowski did a nice poster on this morning. Steve Sain is doing a talk in A32E tomorrow, or rather Wednesday, as is Tammy Griesby, also on Wednesday. Whoa. NARCAP Community. I hope you are all part of it. So basically, we think there are 3 user groups. If you haven't used any of the data, you can still sign up. We have now over 700 users, and over 70 articles have used the NARCAP data for research. And with that, I'm from New York. Thanks very much.
Time for one quick question, if anyone has one for Linda. Yeah, I can't see you, so shout. Go.
Is this going to be the end of this effort, or are you going to take advantage of the 20-fold increase in computing facilities that have become available since you started to do either higher resolution or larger domains?
Yeah, we're discussing, and already, you know, of the Cordex program that is doing multiple domains throughout the world. We're discussing getting the U.S. more involved in that part for over North American. The Canadians have already developed some simulations. Certainly those simulations will be continuous, for one thing, following the Cordex protocol, and certainly higher resolutions will be generated. So stay tuned.
Okay, our second speaker is Stefan Sobolowski. He'll be talking about evaluation of present and future North American Regional Climate Change Assessment Program, regional climate simulations over the Southeast United States.
Great. Thanks very much. Thank you to Linda and Bill for inviting me to do this talk. Change the title a little bit for the talk, I guess. So we'll be using some of the performance-based metrics that Linda was talking about at the end of her talk there to examine the NARCAP simulations over the Southeast United States and see if we can constrain the uncertainty a little bit in the future simulations, especially in this area where there's been a number of slides over the past few sessions that have really shown that this is an area where the models are generally in high disagreement when it comes to precipitation changes in particular. And the patterns for the temperature changes, in fact, when you look at the RCMs, are quite different, and I'll be showing that in the next few slides. So this is work that was appeared in JGR earlier this year. So just to give some quick objectives, motivations, I think the first bullet point goes without saying. Obviously now stakeholders are much more interested in climate information at scales that AOGCMs are not able to really provide anything on. And the Southeast U.S. is particularly interesting because it's been an area that's had explosive population growth and economic growth over the last 20 years, maybe the last 4 or so accepted. And it's resulted in a dramatic increase in demand for water and energy resources that actually have already exacerbated the effects of even modest typical events. For example, the drought of 2005 to 2008 was not remarkable, really, in a climatological sense, but was significant in terms of the damages, and people in the southeastern U.S. still regard that as a sort of watershed event. Forgive me the pun. And that's a picture of Lake Allatoona. Wait, am I using this the right one? There we go. And that's a picture of Lake Allatoona in Georgia in November 2007, pretty much completely dry. So the thinking is that as population growth continues and economic growth continues, and as our infrastructure continues to have issues related to it as it's aging and isn't improving, Sandy illustrated that in all of its gory detail. These combined effects can have the potential to have an exacerbating effect on climate change. So we don't need a large shift in the distributions of, say, precipitation, for example, to have potential effects. But we do want to have tighter constraints on the uncertainty. So we want to see something that's robust, at least. So that was the motivation for this. So there's a quick outline of how my talk will go. First, I have a quick description of the RCM, GCM simulations and the observational data sets we used to evaluate them. Evaluation of the 1971 to 2000 period. A brief description of the performance metrics that we used. It's the reliability ensemble averaging approach that was developed by Georgi and Mearns. And we add an additional measure to this that I'll discuss briefly in the coming slides. And first, we then look at the effective weighting on the present-day bias for the models. Want to see how it performs, if this is something that is reliable to use for the future simulations. And then we'll examine the effects of the reliability ensemble averaging on changes in temperature and precipitation in the future simulations and the effect that that has on uncertainty. And some conclusions and maybe some talk of future considerations if there's time. So really quickly, at the time that this work was done, there were about 6 RCM-GCM pairings available from the NARCAP data portal. There are a large number more now. So it's a relatively small ensemble. This is the list of them. And then for the observational data, we use the University of Delaware terrestrial temperature precipitation data set at 0.5 by 0.5 degrees. So, looking at the present-day simulations from 71 to 2000, this is the temperature. U-Del observations on the left column. Center column is the multi-model ensemble mean from our 6-member ensemble. And the right, we see the bias. And the stippling here indicates statistical difference between the U-Del data set and the multi-model ensemble mean. So we can see that the patterns for the seasonal temperatures, this is winter, spring, summer, fall, the multi-model ensemble is able to capture the patterns for temperature quite well, but they're fairly large systematic biases, almost all negative in almost all seasons. Magnitudes are quite large, about 3 degrees, except for the summertime, where there's a little area of positive temperature bias around the Mississippi River and a little negative bias around the coastal regions. So moving on to the precipitation, same setup here. We see that the multi-model ensemble is not able to capture the patterns quite as well as the temperature patterns. In particular, in the wintertime, it doesn't seem to be, there's a large negative bias, and it doesn't seem to be capturing the moisture advection out of the Gulf of Mexico. And we took a quick look at the moisture flux fields and comparing them to reanalysis, and sure enough, it appears to be borne out in that. But that's about a couple hours of work, so I wouldn't put too much stock on that. I think some more analysis needs to be done on that, and that's there's a paper for somebody. There you go. Oh. There are also large biases along the coastal region in the summertime, pointing to problems possibly with land-ocean contrasts, and also in the mountains in the Smokies, perhaps unsurprisingly. These 50 kilometers is still probably too small, too coarse a resolution to really capture orographic effects, especially steep-sided mountains like the Smokies. So it's not too surprising that we still see some problems in those kinds of areas. But the bias is generally negative for the precipitation in the multi-model ensemble mean here. So, quick look at the spread between the models. It's unsurprisingly quite large, especially along the coasts in the summer for precipitation, along the mountains, and in temperature in both the winter and summer seasons. We see quite large spread of almost the same magnitude as the bias. Interestingly, in the wintertime precipitation fields, the spread is quite small, but this is where we also see the largest negative bias. So the models are in really nice agreement with their disagreement with the observations. Yes, thanks to them for being consistent. So here's really quick the ensemble methodology, the reliability ensemble averaging methodology in one slide or less. This was developed by Georgi and Murins in 2003. There's a lot of literature on this, so I'm just going to go through it really quickly. There are basically two components in theirs. We add a third component that's based on model skill. And the first component is a bias component. How well does the model agree with the UDEL data set relative to natural variability? Second component is a PDF-based skill score, which is how well the model distribution agrees with the UDEL distribution. And then a distance convergence criterion. How close is the model to the future ensemble mean? So first we took these first two criterion and weighted the present day case. And just to see how well the weighting system performs and reduce, if it can reduce the bias, by how much, where, etc. So here's box plots for regionally average temperature and precipitation biases with the confidence intervals. These are pairs of unweighted and weighted biases. And the percentages down on the bottom are the percentages of grid points, which differ statistically from the UDEL data set at the 5% level. And the left is the unweighted, and the right number is the weighted version. And we can see that the reductions, regionally are quite large for temperature, but there's still a large area that in many of the seasons that are showing substantial bias. For precipitation, the reductions region-wide are much more modest, but we see large reductions in the percentage of grid cells, which are showing significant difference from UDEL. So the take-home message is that it works, but it's spatially and temporally inhomogeneous, and that's not entirely surprising. Also, if you look at the PDFs for each of these areas, you see very different responses in different areas. Some places the PDF matches up quite nicely when the weighting is applied. Others the mean matches up, but the shape still is off. In other places, the shape of the distribution is improved, but the mean is not. So, still some work to be done on that. And also, a reasonable question to ask at this point is, well, so what? Does this matter does the skill for present-day climate have anything to do with skill for future climate? And I think this is a reasonable question to ask. And so we looked at we took a cross-validation approach and looked at 20-year training slices and tested it on 10-year slices for any 20-year sequence in the 30-year record, and you see these patterns come up consistently throughout. So it's too short to do a really proper cross-validation, but it gives us some confidence that it's appropriate. So moving on to the future. Time machine. So on the left here, we have the delta change for the weighted change. In the middle column is the root mean square difference of the unweighted change, and so that's the uncertainty. On the right side is the root mean square difference when the weighting is applied. So we can immediately see that applying the weighting dramatically reduces the uncertainty range in the future projections. This is temperature, so the changes are all robust. The stippling here is where the entire confidence interval for the change lies outside of the range of natural variability. And it's consistent through all of them. The largest changes are inland in the summertime, which is the typical greater warming in the interior of the continent than on the coasts, and also into the fall season. And for precipitation, unsurprisingly, it's a mixed bag. Very little in the way of significant changes. Some in the wintertime in the northern states of the region, some around the Mississippi River in the summertime, but other than that, not too much. The unweighted root mean square differences are quite large. In many cases, the spread is larger than the change. And reducing the uncertainty with the weighting has a large effect above, in some areas as high as reducing it by over 50%. And this actually has an impact on the robustness. So what I'm showing here is the same slide as before, but just with the grid cells where the estimated 95% confidence interval does not cross 0. So these are areas where the models are agreeing on, or at least agreeing on the sign of the change. This is after the weighting, however. So if the assumptions are borne out with the weighting scheme, then these robust patterns emerge, and it's in particular the winter increase of about 10 to 15%, and summer decrease of 15 to 20% along the Mississippi River. And 30 seconds. So conclusions really quickly. The performance-based scheme works fairly well, provided the assumptions are borne out. And that's true for any weighting scheme, any bias correction scheme, whether you're doing it before running the models, or you're doing it after running the models, or you're doing quantile mapping. There are a number of assumptions that are taken into account for all of these things, and they need to be borne out for this to hold. Oh, actually, I have 2 minutes. Great. Keep on going. The temperature increase, unsurprisingly, as all of our studies have shown, is well outside of natural variability. It's robust. It's region-wide, as high as about 2 to 3 degrees in the summer, and about 2 degrees in the wintertime. Slight northwest to southeast gradient. Precipitation changes are within natural variability, but with the weighting scheme, they become, in some areas, somewhat robust. And this actually matters because as the changes are for precip and temperature are maxima during the peak energy and water resource demand in summer and early fall. And it's also been noted in recent Van Vliet Nature climate change paper that the warmer water temperatures, particularly in the south, are going to have a negative impact on energy production as well. So again, we have this idea of confluence and these things coming together at the same time and creating problems. And I will not go into future considerations, and I'll end it there. And thank you very much to all of these folks.
And we do have time for a couple of questions. With these lights shining on me, I can't always see if you're raising your hand, but please let me... Go. Yeah. Well, you're second, Adam. Yeah.
I don't know. It's hard for me to tell from over here if it's out of focus or not. It might be.
I found the focus a little hard, too.
Yeah, I think Linda's was a little bit off, too, on a few slides. So, but why was South Florida? Florida was left out. Yeah, the reason we left Florida out was that it's kind of a special case. It's also not well resolved by the global climate models, and so yeah, we just did not want to jump into Florida. It's just.
Can't. Move up. Move forward.
Yeah.
Did you have a question, Adam?
No, let's just, we can talk about it.
Okay.
Thank you.
Try to have a pointer here.
Okay.
Just if I could say one thing, there's a theme running through our talks this afternoon was that we are featuring speakers who are not principal PIs on this program because we wanted to show the diversity of the applications, and a lot of these are oriented towards applications of the NARCAP results as opposed to talking about the changes that occurred. Even the first two talks were getting in heading towards applications, and Adam is going to take us yet further. This is Adam Schlosser, and I won't repeat his title because it's up there.
It's very wordy.
You have the pointer?
Yes, I do. Thank you. Thank you all for coming. I know we're competing against free beer, so I appreciate you all for. That's right. We can do it. And thank you to Bill and Linda for the privilege of speaking to you all this afternoon. So yes, my title is a bit wordy. Really, it's got a lot of words because what I'm going to be talking to you about, some of you may regard as a rather eclectic use of the NARCAP data, but hopefully I'll make clear why we're doing what we're doing. But it's really the overall use of this data is to complement an integrated effort to look at water resource, water impact assessments over the U.S. in the coming decades out to about 2050. And I, along with a bunch of cast of characters there that you see, have been working with what's called an integrated assessment model, and I'll get to that in just a second. In that integrated assessment model, we produce probabilistic projections of various climate-relevant impact variables. What you're seeing here on the left is just a suite of PDFs that have been generated from a range of different climate policies aimed to either stabilize or let emissions go unconstrained for the next century, and you just build a PDF of global temperature. But the real challenge here is just to take that information and to bring it down to a regional scale of information complementary to NARCAP, and see whether we can actually do that. Can we actually use this information in our integrated assessment framework to get at more risk-based assessments of in this particular case, water resource assessments? So this is just to give you another motivating slide schematic of what we're doing here. On the right-hand side, what you're looking at basically is a schematic of a water resource framework that we have developed. I'm not going to get into that in any detail here. What I would implore you to do, if you're interested in the nuts and bolts of this framework, is to see a poster that is being presented tomorrow at the Wednesday. Beg your pardon, Wednesday, by Elodie Blanc and co-authors. She will present the framework in much more detail. But what I just want to point out here is that the framework that we've manufactured here is simply an effort to take a model of the human system, which is basically being represented by economic models, both at the global and at the U.S. Level of detail. We actually have a model, an implementation of the model that represents state-to-state trade and the GDP effects of global policy on the U.S. economy. We take those economic drivers and we put it through an additional set of modules that estimate municipal and industrial usage of water. So we're using information on population, GDP, energy demand, and the like to get at sort of what we think water demands are going to play out in the coming decades. What's also of critical importance, though, is our water supply. Where does the water come from? And that's where our Earth model of intermediate complexity gets into. That's that red bottom box there. We have a model that's fairly efficient. It's able to produce those global PDF distributions that you see. But the challenge that we face is, can we actually garner any information from models or model comparisons such as NARCAP to provide a plausible range of regional climate outcomes that can be used in tandem and complementary to our climate projections side to side with our economic model. The key importance here is that we generate regional outcomes of regional climate changes that are complementary and are integrated with our economic model. So we need a technique, if you will, that's very efficient. We can't run NARCAP models hundreds and thousands of times to produce these PDFs. We need an efficient way to do that. So we have developed a way to use CMIP data, but the real question here is that can we actually use NARCAP data? Can we use the regional details of NARCAP data in this framework? And if we do, there's still an additional important question is, if we can actually do this, are there any salient characteristic features generated in this NARCAP data that is unique? That is, we don't see it in the GCM information, but these salient features are on the scale of the watersheds, the regional water basins that we're resolving here that's shown on the left-hand slide there. All those different shades, all those different colored textures are the water basins, the scale of the water basins that we're using in this assessment. Basically, we have 99 basins over the U.S. that we're using in this assessment. So can we do this? I promise this is the only real hefty equation that you'll see here. This is a technique, so the technique that we're using here is published, it's in press. We've used CMIP3 data to essentially use a Taylor expansion. We've used the CMIP data to anchor the patterns of climate change, of climate relevant variables, in this case temperature and precipitation. And we've asked the question, can we take patterns of change as they relate to the zonal mean of a climate model? And why do we use the zonal mean? Well, it turns out that our Earth model of intermediate complexity only resolves the zonal details of the atmosphere. Some people may view that as a limitation. We view it as an opportunity. And in this case, for the CMIP data, we've shown that we do provide, or using this technique, we actually result in robust features of climate shifts. If you're not convinced of me just saying this, I implore you to see another poster that is being presented on Wednesday as well by Sokolov and co-authors. There was also another oral presentation given today by my colleague Erwin Monnier. If you heard his talk and you're not convinced of it as well, please see the poster. This technique has shown very encouraging results for the CMIP models, but the real question is can we use this technique for NARCAP, and do we actually see features that are salient and add some detail? Last motivational slide. So this is just one result of this regional water resource assessment in the poster that hopefully you'll see in a couple days. What you're seeing here are just using this water resource assessment modeling tool. In one of the boxes, we're able to assess what agricultural demands, how we might see agricultural demand shift in the coming decades. So what you're looking at here are changes, percent changes in agricultural demands as represented by this model that we employ, using not only different climate policies. On the top row of results, you're looking at an unconstrained emissions scenario, and on the bottom panel, you're looking at a rather aggressive stabilization scenario where it's trying to limit stabilized CO2 equivalent concentrations of greenhouse gases to 560 parts per million by the end of the century. You're looking at the climate policy effect top to bottom, but left to right, we've used two different climate change patterns from this technique that I just mentioned. One is a climate model that on a global scale gives you a drier result, relatively speaking, for all global land areas. And another one is one that gives you, relatively speaking, globally wet outcomes. And hopefully what you see from this result is that the differences in these two patterns, you see a greater sensitivity or a greater effect of the pattern shifts of these irrigation deficits by the choice of the pattern that we use and not the choice of the climate policy that we use. So, and again, what this is really getting at is, okay, using these GCM pattern shifts, we see this effect. Do the NARCAP simulations or the patterns that we glean from the NARCAP models, do they give us additional pattern shifts that are of the importance that we see here? Hopefully this is what we'll get to. So here's the data and the methods. This is an ongoing project, so I didn't get through all of your matrix, Linda, I'm sorry. But we have 6 models of the NARCAP suite that we've downloaded. And what it's hopefully done, at least in a provisional sense, is to look at not only different NARCAP models that have been forced under a similar GCM pattern or global GCM boundary forcings, but also just the variations amongst the RCMs themselves. So we have at least a provisional matrix here that can explore how these pattern shifts are affected by not only the choice of your RCM, your regional climate model, but also the GCM that it's being forced by. So we use 2 periods to calculate these pattern shifts, the last 19 years of the 20th century and the middle of this coming century, 2050 to 2069. We calculate this in a discrete form, which is this equation on the bottom left. And for the slides that follow, I just want you to call your attention on the bottom right. This is the assessment from our water resource assessment. These are the total water requirements as we've estimated from our framework. And again, the details are in the poster that I mentioned. But the point being is that a large majority of our total water requirements are very much skewed to the western U.S. And so some of the salient features that hopefully you'll see in the next few slides will emphasize that. Okay, so here's some results. What you're seeing here is a result of the 3 RCMs from NARCAP being forced by the CCSM boundary conditions. I'm showing you these pattern shifts, okay? Now, the pattern shifts are basically showing you that shades of orange are relative to the zonal mean. As global temperature rises, these regions are, relatively speaking, seeing drier conditions, less precip. than they would otherwise. Okay, this is irrespective of the zonal trend. This is just the shift in the precip relative to its zonal mean. Conversely, for green areas, you're seeing increases in precipitation. So the bottom right-hand panel is what we get and what we've used for our regional water assessment using the CCM GCM. We have that in the poster that you'll see tomorrow. The other three panels are just looking at the regional climate models. So a couple of the big picture things, which hopefully you see from this, is that by and large, some of the more salient features that you see in the bottom right-hand corner from the CCSM, the real big drying areas, for the most part, the RCMs capture that. There's at least a fair degree of consistency there. What's probably more striking with relation to the question that I've been asking, or that I posed, is that if you take a look at the western U.S., and again, we're focusing on the western U.S. because this is where a lot of the total water demands exist. And if you look at the western U.S., you see that the regional climate models, not surprisingly, all show a very salient feature over the Sierra Nevadas. All right? There's a real increase, relative increase in precipitation, winter precipitation over the Sierra Nevadas, and they're all pretty consistent in that salient feature relative to the zonal mean. All right? And similarly, you also see features over the Northwest, which is the exact opposite, which is drying, relative drying over the Northwest. Moving right along. So that was wintertime precipitation. The question you might ask is, well, okay, if the Sierra Nevadas see relatively more precip, is it in snowpack or is it just rainfall? Hopefully what these patterns are showing is just at least an insight to that. So what you're seeing is a plot similar to the precip one that I showed you, but for temperature, December, January, February average. And the bottom right-hand panel, again, showing you the pattern shifts that we see from the global climate model. And the other three, again, are the RCMs that are being forced by it. And what's interesting is that if you think about that Sierra Nevada hotspot, if you will, of precip increase, there is a concurrent or a complementary, not a complementary, co-varying or co-located relative warming. Okay, so in other words, as the zonal temperature warms, more and more of that zonal temperature is being focused on the Sierra Nevadas, which would imply that even though you're seeing increased precipitation, this is probably not predominantly in the form of snowpack. There probably is some precip that's filtering into this, and that this could be a severe consequence for how we actually are going to manage water in the coming decades. You don't see that pattern in the GCM. So again, this may be a salient feature that we're missing by using this GCM approach, which we may actually gain some more insights by using this the information from the RCMs. Moving along, just to give you at least a complete demonstration of all the RCMs that we're looking at here. This is just giving you results of precip patterns for both summer and winter precip for the MM5 forced by the GFDL model. Similar to the previous slides, you see some very there's some large-scale features here that are represented quite well, not only in the GCM pattern, but also reproduced in the NARCAP pattern, with additionally, similar to the other RCMs, this enhanced salient change, either in the positive or the negative, over the western U.S. or the west coast of the U.S. And last but not least, this is just giving you some results for the two models that have been forced by the CGCM3. This is probably an interesting, very different in terms of some of the characterizations I've just made, is that when you look at the bottom panel, which is the GCM pattern, and you look at the top two models, the RCMs, while they may in some way, if you've taken up steps back, you could see that there is some agreement in the overall pattern, maybe at least in sort of a colder ocean, warmer land sort of effect. There is this salient tongue right through the center of the U.S. that the MM5 model actually is saying, well, there's actually a relative cooling over the central U.S., as opposed to the CRCM, which says, actually, no, I want to enhance that cowl pattern, that colder ocean, warmer land pattern. So while this, thank you, yes, I'm almost there. While this may actually emphasize, well, we have a lot of uncertainty here, what this really says is that there's risk. All right? We need to use these patterns in a Monte Carlo framework and ask ourselves the question, is this uncertainty, how does this uncertainty translate to risk? So how do we do that? Well, unfortunately, that's grounds for future work because I've run out of time. But hopefully what I've shown you is at least in a provisional sense, a demonstration that the pattern scaling technique, essentially, that we've used for GCMs, we feel fairly confident that this technique can be extended to incorporate this NARCAP information, and that we do see evidence of salient features on the scale of the basins that we're running that may actually allow us or give us further insights or a broader range of uncertainty, which will translate into risk. We have employed this technique in a study over the Zambezi River Basin where we've done the full end-to-end simulation suite and have generated PDFs of GDP shocks over Mozambique. Our ultimate holy grail goal is to use this information, run our water resource model through a large ensemble of plausible outcomes to hopefully arrive at assessments of risk. So with that, thank you, and I'll take any questions if there's time.
Time for one quick question. I just want to ask, if you were able to use the more complete NARCAP ensemble, would you be able to maybe tease out a little bit more the contributions from GCMs versus RCMs in all of this?
Actually, yeah, the previous presentation I thought, or I think it was, where you had, or maybe it was yours, Linda's, where there was winter and summer. Yeah, I think that would actually be a really nice complement. But I think we're seeing consistent results that our wintertime temperatures seem to be a bit more aligned with the GCM as opposed to the summertime temperatures. So, yeah.
Thank you.
Yes.
Did you?
Yeah, I did it like before long time. Oh.
Oh, it's on this one. I'll switch.
Yeah,
I'll give you a
I got
warning in 2 minutes. Okay, our fourth speaker, Yongchang Liu, from working with Linda, and again, you have the title up there, so go ahead.
Okay, thank you. Yeah. Okay, today I'm going to talk application of NARCAP climate change scenario to forest fire. How to move forward?
Oh, sorry. That. If you want to move back the keyboard.
Okay. One of the missions with U.S. Forest Service is to keep the health of national forest system, which will benefit the nature and people's life. But there are a lot of forest disturbances. Fire is one of them, which will threaten the health of forest system. Especially in the present, in the past about 20 years, this threat from fire has been increasing. If you look at this, in the past 50 years with the red line, the fire has been increased by about 50% in the past about decades. Fire also threatens human life, also cause like huge damage in economic and social aspects. What I want to bring your attention is the last one, which is how many people, firefighters were called for the big fire in 2002 in South California. So the task for Forest Service is to call firefighters from local or even nationwide if the fire gets uncontrolled. Then we have another big problem, which is climate change. Because of atmospheric condition is one of the major factors of fire, especially for fire variability and change. So because the increased temperature nationwide for the United States also, many areas will have increased frequency or intensity of drought. It's very likely the fire will increase under the changing climate. Actually, there are several research which already show, one of them showing in Rocky Mountain region, by the end of this century, fire will increase by 150%. The purpose of this study is to use the NARCAP regional climate change scenario to analyzing and projecting fire. Specifically, three things to be accomplished. One is to look at the current spatial patterns and the trends over the past 30 years. The second one is to look at what's the trend in fire in the future and the changing climate. And last one is to see what's the spatial relationship between fire potential. For example, if there is a fire in South California, what's the possibility for other regions like the Southeast, the fire will happen at the same time? We will use an index called KBDI to look at the fire potential. This index is calculated based on two meteorological elements. One is maximum temperature, which is based on daily observation or simulations. Second is daily precipitation. We also use long-term average precipitation to be used as a surrogate of vegetation conditions. So there are a range of values for KBDI from 0, which means no fire rate at all, to 800, which means very extremely high fire potential. So NARCAP data we used, right now we use only one GCM and regional climate model combination, which is a hardware center model. Here is an example for 2007 volcanic fire in North Florida and Southern Georgia. So you see this area, there was very extremely high fire potential from KBDI. For the spatial relationships, we use two methods. One is common used EOF to see the spatial pattern and also how this pattern changes with time. The second one is so-called probability of co-occurrence of high potential. There is a step to calculate this, but I just want to mention that we divide the nation into 8 regions. So for each region, like Pacific South, we choose one point in the middle of this region, then do the calculation with other regions. Only calculate when the fire potential is in top of 20% percentile, so which means it's a high potential. Okay, this is a spatial distribution of fire potential for 4 seasons. So basically, we see the high fire potential in the west region, except the Pacific coast. Then there is a decrease toward the east. For the eastern United States, there is very low fire potential in winter and spring, but will increase during summer and fall time. Basically, will reach a moderate or even high fire potential during summertime. Then this is for future. So we'll see a big change or increase in the Rocky Mountain regions, for some southwest and mountains, or even North Plains. So most changes will be in summer and fall seasons, especially for the central, the middle of eastern United States. So what does this change mean in the future? Right now, we have fire potential basically either it's moderate for the western United States, or the low fire potential in the eastern United States. But if we count in the increase in the future, this region will increase by 1 level of severity, from moderate to high, or from low to moderate. Also, we see the increase trend both in past or in the future. Here, the red line is for present time, and the green is for the future. We see the line here. So what does that mean? Number one, there is already happening of the impact of climate change in the past like 30 years. Number two, current change rate actually is almost, if you look at this is for national average. Then the number shown here is for each region, 4 different seasons. So all seasons and all regions except the 2 in Southeast, we see this kind of increase trend in the past 30 years. Basically, we use the 2 meteorological elements. One is temperature, the other is precipitation. So this shows like the 3 bars for each region. The red one is both elements were used. Then next is used only temperature. The last one is only used precipitation. Basically, there's almost no change with using only temperature, which means the temperature is a major factor contributing to the variability or change in fire potential. So this actually is very meaningful because like we have a lot of models, there is uncertainties, but basically the uncertainty is relatively low for temperature projection than in precipitation. So the calculation of fire potential is kind of like reliable from this. So for spatial pattern, this is EOF pattern on the left, then this is a time variation on the right-hand side. This is for spring time at the present time. This is for future. Basically, the first pattern contributes about 20 or less than 20% of total variations. The first pattern basically describes like a kind of uniform pattern across the United States. One thing I want to show you is you see this kind of trend, like a decreased trend with time. This is also can be seen for summertime. You see this trend. The opposite sign because the sign for spatial pattern is different. So basically, this just confirms what we have seen for the real fire potential data, which means fire potential has been increasing in the past 30 years. But strangely enough, like you see the future, this kind of change actually is less significant. If you look at the pattern, it's kind of uniform. But in future, there is like a spatial variability. Also, if you look at the contribution, for now it's like 20%, 26%, but the future is less than 20%. So this kind of uniform or spatial degree of spatial relation is reduced in the future. This is use current probability to measure the spatial relationship. This is for spring, again for current time and the future. So we see for a number of reasons, a number of regions like southwest, northwest, south central, north central. If this region has a high fire potential in springtime, then you will see a high possibility. Like for other regions, we will see the high potential, fire potential as well. This is for spring. Then for summer, this kind of spatial relation is even higher. See the extent, like for this region. This is central, south central. Here, there's extended fire to fire potential in southwest and northwest. But if you compare present time and the future, you see for these regions, generally there is a decreased degree of spatial relationship. Like for southwest, in the future, the relation is found only for the southwest itself. This research only used one model combination, GCM and local model combination. But we do compare this combination with other models at 2 specific locations. One is in like a central plain area, the other is in southeast. So here are 2 points on top and the bottom. Then for springtime, I'm sorry. This I moved too fast. This is another way to show the regional average of probability. So this clearly showing the big decrease in a spatial relationship. Like for southwestern spring, you see the blue bar is for current time, the red bar is for future. So you see the decrease almost reduced by 50%. And this is for northwest, the same thing. Okay, this is the comparison between the model combination we used, which is the last column. It's a cardless hand model with other model combinations. For one point in the central plain, the other is in southeast. So basically for the north plain, the signal is pretty much similar except one model combination. But the magnitude is really small. And the same thing for the other gray point. This morning I saw a post by Nasra. It says yeah, he showed like a system bias with this model. Okay, I just got like a higher bias from this model for the northwest area, but unfortunately he didn't show for this 2-point area. So, but we will look at this in the future. Next. So basically, what we learned from this study, number one, NARCAP data has provided very useful value for doing like 5 potential projections, also analysis. And number two, in the future, the current 5 potential has increased. Also, this is kind of a trend where it continue in the future due to the climate change. And we see the 5 potential spatial relationship in several regions, especially southwest, northwest, and south central. But this kind of relation will be reduced in the future. And we see some difference between the model we used with other models. So next step, certainly we need to calculate this 5 potential using all available GCM and regional climate model combinations. So with that, I would like to thank you for your attention. Also, I would like to mention the funding support from National Fire Danger Rating, Joint Fire Science Program, which provide funding support for this study. Okay, thank you.
We have time for a couple of questions. I had one question. You mentioned how that spatial coherence decreased in the future. Have you looked to see if that's connected to changes in precipitation patterns, or what factor would cause that to happen?
Not yet, but we discussed like kind of this, because this result first surprised us because we look like assume everything will be increased in spatial. It's like a time variability, also spatial variability. So if spatial variability is increased, that kind of explain this. But we didn't look at the data yet. So I guess that is important. We have to look at the data to explain why this happened.
Okay, thank you.
Okay.
All righty, next up, we have, let's see, where's my list? Brad Horton, who's going to be talking about extreme temperatures and their mechanisms in NARCAP simulations. Yellow light means gone through 13 minutes.
Okay. And how do I advance? Ah, good. Okay, but this just clicking on a little bit. Okay, that's right. Okay. Thanks, Linda. Thanks, Bill. I'm going to talk about extreme temperatures and their mechanisms in NARCAP simulations. This is work through a team at Columbia and NASA Goddard Institute for Space Studies. The work is supported by the Consortium for Climate Risk in the Urban Northeast, which is part of the NOAA RESA program, bringing climate research and climate information together with decision makers of various types. In our case, focusing very much on the urban stakeholders of the Northeast, Philadelphia, New York, and Boston. And so some of their climate information needs have informed our research directions. One thing we've been hearing a lot, as I think everyone has, focus on extreme events. So what are some of the reasons to study temperature extremes, and particularly maybe to look to NARCAP for that? Well, within our CC run domain, human health is a major component. We're engaging, for example, with the Department of Health in New York City to look at impacts of heat waves. Heat waves being the greatest weather-related cause of death in the U.S. Built infrastructure, a lot of the aging infrastructure of the Northeast is particularly vulnerable to heat waves as well. And there have been recent observed studies and modeling studies of various types of outputs suggesting that temperature extremes could warm in the future at a different rate than your sort of average temperatures might. And that's important because I think some of the foundational research, some of the research certainly that we've done in the Northeast has initially focused on average changes in global climate models or regional models and applying those average changes to the historical daily distribution. But if we're finding different results when we go to that sub-monthly daily distribution, that could have big impacts on the frequency, for example, of heat waves or extreme cold events. And certainly some of Linda's work and many others has shown that as we go to the finer resolutions, as might seem intuitive, there is some hope of resolving some of the key climate extremes better as well. Okay, so quickly on the methods, what we really focused on here was what we defined as the once per year extreme heat or extreme cold event, something that happens often enough to be experienced frequently almost by definition by stakeholders. And again, given some of the vulnerability of the infrastructure, for example, in the Northeast, something that happens once per year is sufficient often to cause a lot of disruption of various types. So the way that was defined, basically, if we talk about the once per year, is if we have a 30-year data set, we just took for T max, we took the 30th highest ranked value and called that the once per year. We focused on just JJA, June, July, August for our T max. For T min, we focused on winter DJF. So of course, to define the once per year coldest event, we ranked from bottom to top among DJF the T min values. Calculations were made separately for each grid box, and I'm going to focus here, I highlighted in bold, I'm focusing on the ensemble results from NARCAP, but as we've already heard, when you go to the individual RCM members, we get a very different story, but all the plots I'm going to show here, I wanted to emphasize are the ensemble across these GCM-RCM pairings. And as a last step, we converted the results to a common grid at half a degree to enable comparison. And some of the results will show sort of the standard set of 3 sets of NARCAP simulations. A lot of the analysis will focus on the GCM-driven simulations that we heard some about. I focused on 5 where we have maximum, minimum temperature, and snow water equivalent available. Okay, so starting into the analysis, what we found for winter minimum temperatures, first a little bit of validation, comparing 2 different sets of historical or hindcast, in a sense, RCM simulations to daily observations from NAR, the North American Regional Reanalysis. So each of these is a difference plot. On the left, you see the ensemble of the NCEP-driven RCMs minus the NAR. And on the right, you see the GCM-driven RCMs minus the NAR. So in each of these cases, you're seeing that once per year coldest T min. And the color bar is a little funny on this, I apologize, but values between -2 and 2 Celsius, which we might think of as a relatively good job by these RCMs of capturing NAR's results at least, are showing up as yellow to red. So on the left with the NCEP-driven, you could argue for much of the U.S., pretty good job of capturing this once per year simulation. As we go to the GCM hindcast-driven RCM results, though, we can see a large part of the western part of the U.S. with very large biases in that once per year T min number. Okay, so now what happens when we go to projected changes, when we look at how T min values change in the 2050s, that 30-year time period for the A2 simulation, relative to the GCM hindcast base periods. So what you see on the left is, again, that once per year T min value, the cold value that you expect to experience at each of these grid boxes on average once per year. On the right, if you just took the T min for every single day in winter and averaged that, future minus base. So anywhere where the values on the left are red, that's suggesting more warming of that once per year T-min than what you're seeing, for example, on the right in the average T-min future minus base. So the next plot is going to be subtracting the plot on the right from the plot on the left. So anywhere here that you see some of these red colors, that suggests again that that once per year T-min is warming more than your average T-min on your sort of typical winter day. And we found that, and then you see a histogram of those results averaged across the whole U.S. on the right. So for 96.5% of the grid boxes in the U.S., you had more warming of that once per year T-min than you did of the average conditions. And you can see for some parts of the U.S. on the order of 2 to 3 Celsius, even like 5 degrees Fahrenheit or so, over relatively large areas. So we're in the process now of trying to explore some of the mechanisms to see if this looks robust. We haven't gotten that far with it, but I wanted to at least sort of point to some of the things that we're looking at. We wanted to start with snow water equivalent. Are there some albedo feedbacks that might explain some of this? Moisture feedbacks potentially associated with snow cover as well. We want to get into a dynamical analysis as well. Are there changes in circulation that can explain it? But it's a little tricky because, as I mentioned earlier, we're making these calculations separately for each grid box. So as a result of that, when you look at those maps, you can't view it as a particular day. One grid box is, 30th coldest day. Might be an entirely different day, than some other grid boxes. So we're looking into how to do that dynamical analysis, but a typical sort of composite dynamics plot isn't getting us that far. So quickly, just to show a little on the snow water equivalent. So the top two plots are the ones I showed a few ago. I won't go back. The T-min change in the once per year on the top left, and then the change in the average T-min, your typical winter day, top right. And then the equivalent comparisons on the bottom, but here for snow water equivalent. So anywhere you see green, for example, in the bottom left, the once per year coldest T-min is associated with more snowfall on the ground in the future, if you see green. And then in the bottom right, those are cases where on the winter average you're seeing snow water equivalent. And in that case, it's going down in almost all cases. So a couple sort of quick things. Again, we're sort of early into this analysis, and if you see also towards the bottom of these maps, there's a lot of places where we have a mask. Anywhere where you didn't have where you had less than 0.5 centimeters of snow on the ground, snow water equivalent on the ground, either in the base period or in the future, we masked those out. So the mask is bigger the mask is smaller for that once per year T-min, suggesting that there's more snow on the ground in general when you have a really cold day than in your sort of typical winter day. But then when we look at the change, the actual information contained in that plot, sort of bottom left or bottom right, you can see a little bit larger area showing an increase in snow cover on the colder day. Really almost no area showing an increase in snow water equivalent for that typical winter day. Although there are a few places, sort of northern Minnesota, that are very cold where in the future the snow water equivalent seems to be staying about the same. So we were, I think, sort of hoping or wondering if we might see some of those areas that are in green, for example, on the bottom left, corresponding to slightly muted temperature increases in the top left. I think we haven't gotten that far there. But there are a few places where that might be the case. Some of the mountainous areas of southern Pennsylvania, for example, have a little bit of a muted temperature increase, and again are showing more snow cover on the ground. So there might be some albedo feedback there that we're exploring. Okay, so just to quickly hone in on a couple examples now in the mean changes. Typical winter in the future minus typical winter day in the base period. So we show an example from Pacific Northwest and also an example from Minnesota. So if you look at the base period in the ensemble, the temperature for this particular grid box in eastern Washington was about 28.7. As we go to the future, it goes up to about 33 degrees. Large change in the snow water equivalent, perhaps associated with this phase change right around 32 degrees. Now, if we look at one of the grid box in northern Minnesota. Here we have the base temperature 6.5 degrees Fahrenheit, goes up to 12. No decrease in the snow water equivalent there. It stayed about the same. Okay, so just do a quick run through of some of the findings for summer maximum temperatures now. So here, again, the once per year hottest on the left, change in the once per year hottest temperature on the left for each grid box, change in the average Tmax, taking all the days in summer in the base period and comparing those to the future. Excuse me, I'm sorry, this is first the validation slide, I apologize. This is comparing the NCEP-driven once per year Tmax to the NAR reanalysis once per year Tmax. And then on the right, the same with the GCM driven. So overall, the biases appear to be smaller for the Tmax than they were for the Tmin. But still, in some cases, for example, parts of the Midwest, pretty large biases here as well. For the GCM-driven case, actually a little bit smaller, it appears, in the NCEP-driven. Again, this is in the ensemble. If you look at the individuals, we see a broad range of results. Okay, so what happens now when we look at the changes in the future? GCM-driven change in the once per year Tmax on the left, and then your average typical sort of Tmax for a summer day on the right. Again, as we saw with the Tmins, large parts of the country showing more warming of that hottest day per year than they're showing for the average summer day. Here you can see that difference again. So this is the plot on the right, minus the plot on the left minus plot on the right. Large parts of the Northeast here showing more warming of the once per year Tmax. And then that histogram is actually just focusing on the Northeast in this case. So 91% of all the grid boxes in the Northeast had more than 1 degree more warming of the really hot days than they had of the typical summer days. So we think that's potentially important because so much of the research in the past has just used a delta method type of approach where you just looked at the shifts in the typical summer day without considering how the distribution of temperatures within a month might change. So if we go a little further and look into the recurrence curves, we can see how that impacts the results. I don't have time to go into it, but these are the types of mechanisms that we're trying to get into to explore why the extreme temperatures might be changing more, looking at fluxes, soil moisture, and also dynamical analysis. Am I at 15 minutes or going to 12 minutes here? 2 minutes. 2 minutes. Okay, I'm almost done. So if we look now at changes in the frequency of these extreme events, if you look at the GCM-driven RCM hindcast, those base period in the RCMs, the once per year extreme heat event is about 95 degrees Fahrenheit. Now, when we look at the GCMs in the future driving the RCMs, 95.3 degrees Fahrenheit happens about 10 times per year. Now, if we look at the observed baseline, which and I need to say this is a New York City grid box. This analysis here is just New York City. If we look at the observed baseline, New York's historical data, you get 95.3, about 3 times per year. The once per year event in the observed data is about 98 degrees. If you just applied that delta method, the changes from the RCM, summer means, that would go up to about 13 times per year. So it's a little hard to tease out from here, but we think the suggestion is that by including the daily data from the RCMs, you could get about double your frequency of extreme events relative to what you'd get if you just looked at changes in your mean summer temperatures. Okay, so final slide, I just wanted to say a little bit about where we're going from here. Clearly we're seeing that shifting the mean and shifting the distribution can both have very large impacts on the frequency of extremes, maybe even equal impacts. And so we're looking at now how can we build more confidence in these results. As we heard, it's a small set of GCMs, small set of RCMs. We're looking to go further with the mechanisms, but we're also thinking about stepping back. Are there other sources of uncertainty that we can also try to capture? Whether looking at a broader suite of GCMs than the 4 shown here. There was a recent paper showing that if we go to a really large pool of simulations with one GCM, you can get a pretty broad stream of results just by changing your initial conditions. And then also we're looking at issues of things that GCMs still aren't capturing that well at all, even if you go to a large set of GCMs, sea ice loss in the Arctic being an example there of something we want to explore, how that can impact mid-latitude extremes.
Great, thank you.
Thank you.
All right, anybody have a quick question?
Did you check your block maximum minima approach to make sure that you're not missing multiple extreme events in 1 year and possibly capturing events in another year that are actually not particularly extreme?
Yeah, so what we actually did was a full ranking of the 30 years of data. We just grabbed the 30th ranked value. We didn't do a calculation in each year.
Okay.
Yeah, so we were trying to get the true once per year. But you're right, if you take the approach of just averaging for each year, you get a pretty different result. Yeah. So, do you have time? Okay.
Sure.
My question is, the different rates of Tmax compared to average T, is that a result that's also seen in GCMs, or is that unique to NARCAP?
So yeah, I think that's the key topic we got to ask next, because this doesn't show the extra added value of the RCMs. I don't know if others have a comment on that, but that's something we're looking into. Good question.
Okay, great. And conveniently enough, our next speaker is Chris Anderson, who's going to be talking about the use of NARCAP data to characterize regional climate uncertainty and the impact of global climate change on large river fish population. Missouri River sturgeon example.
There's a mouse.
Close this.
I'm sorry, I don't understand.
Great. Looks good. Thank you.
It turns yellow, you have 2 more minutes.
Okay. Okay, so that's a very, very long title. And I want to start off by explaining what I think the most important objective is that we've obtained from doing this work. And then what I will do in my presentation is step through the algorithm that we have developed. And then there's one slide that transitions from the algorithm to the results. And on that slide is an illustration of how the algorithm fits within the mathematics. And then finally the results. And so in my opinion, the most important thing we have accomplished with this work is that we have developed an uncertainty quantification method. With this method, we're able to integrate the regional climate variability with process model variability, with parameter estimates within the process models themselves, uncertainty, and finally express all that within a stochastic model for the population of sturgeon. So this ability to integrate uncertainty and watch it go through the different components of the modeling system is what I believe is the best thing that we've accomplished in this whole work. And so as I said, I'll step through here. Well, I might say also that our project director, Mark Wildhaber, is a fish biologist, and he may disagree. But on Wednesday, you can go see his poster during the Climate Science Center poster session, and you can see what he is thinking all these results actually mean for fish population. So as I said, I'm going to step through the algorithm a little bit and read a few of the slides because I want to make sure I get the words correct. So what we use NARCAP data to accomplish is this. We want to evaluate the possible pallet sturgeon population response to climate change by faithfully accommodating uncertainty from models, data, and expert knowledge. And how we did this with NARCAP data and how NARCAP data are ingested into the process is we quantify uncertainty propagation through linked process models for climate, stream flow, stream temperature velocity, and pallet sturgeon population. And I want to emphasize that the sturgeon population model is a stochastic model. The NARCAP data are used to establish the regional climate variability that is going into our linked process models. In particular, we use daily data as input to hydrological models and daily temperature data as input into water temperature models. And again, I'll emphasize that the results that I'm going to show later are from early developmental stages of this modeling approach, and they're very preliminary. you can see Mark Wildhaber's poster on Wednesday that gives the most up-to-date information. So the goal of our research is to examine how future climate conditions might influence sturgeon population, and again, preliminary work, and very exploratory. And what we need to understand is on the lower right are the circled regions along the Missouri River where there are currently management plans in effect for sturgeon population. And much of our work actually is going to focus on down here, and you'll see the results in Mark Wildhaber's poster that focuses on this particular region. Now, there are many ways that climate change could potentially alter the sturgeon population. It could alter the habitat conditions that are suitable for spawning. It could alter the embryo growth via changing the water temperature. It could alter the energy expended while sturgeon are swimming. It could create different migratory constraints than they have nowadays, or it could change the amount of prey that's available for sturgeon to eat, which is the thing that allows them to grow. In this particular study, we're only looking at the energy expended and how that will affect its growth rate. In the lower right-hand corner, you see an example of sturgeon populations today, right now. The white bars are sturgeon in the wild, that is in the river itself, and this is on the x-axis the size of the sturgeon, and on the y-axis the number of the sturgeon. And then in the shaded bars is the sturgeon population within fisheries. And so what happens is that they would like to release these sturgeon, and they would like them to grow into these kinds of sturgeon that are much larger, and in order to propagate the species forward in time. So in this particular study, we used a bioenergetics model that was developed by a student working with Mark, or a staff member working with Mark. And this, as I said before, is a stochastic model, and you'll need to talk to Mark to really get the details of it. But basically, it has two components that relate to growth. One is the amount of food consumed, and the other is the respiration as the fish are swimming. The food consumption is parameterized relative to water temperature, and the water temperature relates to what kind of prey is available and how quickly, I think, how sturgeon may be able to move around. The respiration has to do with how much energy their body is actually expending while they're moving around, and that's related to water temperature and water velocity. Well, water temperature is further a function of air temperature in the climate, and water velocity is a function of stream flow. And so this is kind of how all of our models link together. We start with the global atmospheric ocean models that provide the global circulation and then the coarse representation of the regional climate. And then that links into a regional climate model which refines the regional climate simulation. And in this case, of course, we're using NARCAP. And then this goes into a basin hydrology model which gives us runoff and stream flow. It also can give us stream velocity. And then we take data from the stream flow to really get the stream velocity, and also data from the regional model to get the stream temperature. And all of this ends up integrated into the bioenergetics and population model. And this is a little bit more specifically what we did for this particular presentation. Here we only used one of the NARCAP models, the Canadian CRCM, and we used the two simulations, one from the CCSM, one from the Canadian GCM, that went into the Canadian regional model. And some of the daily data go into the HEC HMS model, which is the streamflow model used by the Army Corps primarily and developed by them. The results of the training and application of the HEC HMS are under review right now, and Ted Moran is the person who is doing all that work. Then we take not only the daily data and put it into the streamflow model, but we also take the daily temperature and some sunshine information to go into the stream temperature model. And we actually tried two temperature models, one called SMTemp and one an empirical estimation based on historical data. From the stream flow, we get channel routing to get stream velocity, and that information goes into the bioenergetics population model. So how do we integrate the uncertainty? Well, we use hierarchical models. So intuitively, if we're interested in the distribution of consumption, how much is being eaten, or how these distributions of fish are growing through getting their energy from eating, then we have to take into account the uncertainties in the maximum temperature of the air and the temperature of the water. And intuitively, we could take samples from the maximum temperature of the air, which would come from the climate models, and we run those maximum air temperatures into the water model and feed that into the consumption model. However, what happens is that this would give a distribution and that would reflect uncertainty in Tmax, but it would not address uncertainty in the water model formulation itself, as well as the stochastic component of our consumption model. So this is the one equation that transitions, and it shows how we use these hierarchical models. In this equation that's 4 integrals, we have 2 conditional distributions. And when I talk about a hierarchical model, these conditional distributions are the hierarchies. And what we do instead, what I described on the previous slide, is we would take a sample from Tmax distribution, shown here with a bracket without any bars indicating there aren't any conditioning with anything else, and we would put that into the TW. And so this would look like TW given Tmax. And then the TW would go into the C. So this would look like C given TW. But what we have done instead is we have allowed for the parameters of the water temperature model to be varied. So we can look at the distribution of the parameters of the water temperature model. That's the theta. So they have their unconditional distribution, but once we sample from both Tmax and theta W, then we get a hierarchy of the water temperature model providing a different distribution. And then we can sample we can sample from that hierarchy to provide the next hierarchy with water temperature, but what we have added into it are samples from the parameters of the consumption model, which of course they do have their unconditional distribution, but when combined with the water temperatures provide us with the next layer of the hierarchy. Then when you integrate all that, that means you get the uncertainty from the parameters of the consumption model, the parameters from the water model, as well as the variability of the climate through the maximum temperatures. The genius behind all this is Chris Weichel at the University of Missouri, and he's someone that you would want to talk to about that rather than me. So here we are with our results, and the way we have done this is that there are samples of pallid sturgeon and distributions of what pallid sturgeon population is in the Missouri River. And we've taken an actual historical empirical distribution as an initial condition in this approach. And so we take 1,000 samples out of that empirical distribution, and then we put it through that linkages of models to come up to see how that initial distribution changes. And then what you'll see is how the distribution properties change as well. The scenarios we ran were, they include the base, just the observational data, and for those in the room who know the VIC, historical gridded data set, that's what we use for our observations. And then we just have 3 simulations that we've included. CCSM and CGCM of the contemporary climate, the retrospective or historical, I can't remember the terminology used in the previous presentation, but kind of the historical simulations, and then 1 future simulation. Just to give some context of where the CRCM what it looks like relative to other downscale data sets, these are time series of 30-year average rainfall for, I think, primarily over Iowa that I've plotted just to look at how the precipitation change in NARCAP compares to what's called the asynchronous regression regional model developed by Ann Stoner, Catherine Hayhoe, and others. And this dot here that's underneath the squares is one CRCM model, and this dot here is the other CRCM. The purple dot on the bottom is the other CRCM model. So you can see that it lies pretty much within the distribution of other downscale data sets. And I've also compared it here quickly for March, April, and May precipitation and temperature change to the so-called BCSD data set that looks just at monthly downscaling. And the CGCM change, or CRCM changes lie pretty much right in the middle of that entire distribution. The one that was driven by the Canadian models is a little bit not as wet as the mean of all of these points, so maybe it's a tiny bit drier in the amount of change it's predicting under climate change. But in all, there isn't anything extreme or unusual about these two chosen regional climate simulations. And so here's one of the great results. Here's an example of looking at the parameter uncertainty versus the regional climate uncertainty. And so the black line is our initial distribution of sturgeon. The red line is the updated distribution of sturgeon given one setting of the P parameter where it's updated annually. And the blue line is when it's updated daily. And what you can see, if you compare the right and the left, is that the current climate, 1980 to 95, compared to the future climate, 2039 to 2054, has similar blue and red lines. But the blue and red lines are separated more than if you go over time. And what that means is that the parameter, in our developmental stages of this modeling effort, we found that there's a parameter setting that has more of an impact than the regional climate variability. And then second of all, we replaced, as I said in the beginning, our temperature model for the water temperature. And a similar result is found. In this case, I'm just going to point to the bottom as opposed to going up here, which is cross GCMs. You can see that the blue line is pretty similar in the contemporary and the future. The black line is a little bit different, but really there's more separation between the blue and the black, which represents different water temperature models, than there is between the current and the future. So in our developmental stages, early preliminary work that we did here, we found this uncertainty propagation mechanism to be really helpful to identifying whether or not there are parameter settings that were, and model choices that were more important than the actual climate change itself. So the potential uses of this framework, I believe, we've demonstrated this within the bioenergetics population model, but that doesn't mean we couldn't also link it to other models, such as for habitat and migratory constraints and whatnot. And so I believe it has the capability to directly link projections of climate change with current and hypothetical management practices, if there were appropriate models to be ingested into the hierarchical procedure. And then finally, we could clarify a little bit more, and we've talked about this and looked for funding, by incorporating within the hierarchical structure some simple physical models to understand why the climate models are different in their physical simulation, or their simulation of the physical climate. And so I'll stop there and take questions, and thanks.
Okay, we're running a bit behind, but does anybody has a quick question? Yes, sir. Yes, you. You.
Yep. That's correct. No, we haven't done it over the entire suite of the models. It was just that one test sample that we did. That's right.
Okay, great. Thanks very much, Chris. All right, moving right along here so that we can get out of here at a reasonable time. Ernst Linder will be talking about downscaling NARCAP model output for local level impact assessment.
How does this go?
After 30 minutes, the yellow light will go on. Okay, all right.
How do I follow this? Okay. And the slide, how do I? Oh. Do I change the slide? Just push down. Yeah, okay. All right. First, I'd like to thank Linda for inviting me to talk here. So this is my title. I added a line, Daily Precipitation in New England. My title was rather generic. I'm used to talk at statistics meeting where methodology is more important. So I also wanted to acknowledge my students, Eric Laflamme and Yibin Pan, who contributed quite a bit of work to this. This is ongoing work. So first of all, we are motivated by collaborations with engineers who are interested in, who are working on infrastructure design in the future. And they have various process models that work at fine scale, temporal scale, that's hourly to daily, and also at a a particular location, for example, the location of a dam or the location of a street segment that's being paved and so on. So we got involved in this, and there was a need for downscaling. And so we're concentrating on precipitation because that's a little bit challenging. So what we're trying to do is we're trying to examine the patterns of downscaled future daily precipitation based on NARCAP projections of those 30 years. Our focus is on extremes because extremes are the worry in New England particularly. Some questions one could ask: is there an upward trend compared to current data? Is there a consistency across NARCAP models? These scientists, they're interested in which model should I choose for my design, and so on. Uncertainty. We are doing a full uncertainty quantification, just like in the previous talk. And in the end, if I have time, there's a little bit on, we try to validate how valid is our model, our downscaling method. Oops. Oops. Oh, yeah. All right, thank you. Why New England? Well, New England is home for us. University of New Hampshire is in New Hampshire, and New Hampshire is in New England. I used to have mathematical symbols for that, but they didn't work. This is historic and current trends are well studied. I'm going to cite 3 of those studies. One is the Carbon Solution New England, frequently cited study on trends in extreme precipitation for the northeastern U.S. Here's one graph from that study. It shows the changes from 1948 to 2007, and you see red is increase in precipitation. It's mostly more red than blue, but of course not all red are statistically significant. So in this study they did do a statistical analysis. Next is Douglas and Fairbanks, a recent study. They studied precipitation 1954 to 2008, and they did a non-parametric trend estimation and tested for significant increases in precipitation, and these were annual daily maxima. And you can see also there are not that many that are significant, so there is a bit of a question about statistical significance and so on. Back to the Spear and Wake study, they did an annual average of over the northeast, basically, that included New York and Pennsylvania. You see the average precipitation. There seems to be an increase. However, if you look from about 1970 onward, it doesn't look so much increasing anymore. An older study looked at, by Hurt and Hale, looked at global climate models and their predictions for annual precipitation. And you can see there's considerable difference in what the global climate models predict. And if you look at really the sort of the, and those were ensemble, I guess, uncertainty bands. If you look at those, there could be considerable difference going from like 60 to 120, almost doubling if you look at the extremes. So there is a bit of a question and about about the uncertainty. So to our method then, we are downscaling RCM output to station data, and we use the NCDC hourly precipitations from 58 stations in New England that had enough data that we could trim to the NARCAP temporal range. We accumulated these two daily totals. We used the RCM outputs, of course, current and projected. And just for the notation, so the station data is the Y series, the RCM output is the X series, and C is for current, P is for projected. And we used 8 pairs of RCM-GCM combinations. We'd like to use all 12 of them, but they were not quite available at the time. So we're using the nearest to station grid point. From these NARCAP models have different grids, unfortunately. So the probability distribution transfer, that's the method we're using for downscaling. This method is, it's been mentioned before, it's similar to quantile transformation or quantile translation. But it does more than that. It uses all 3 available series to translate to the predicted series. So, and of course the assumption is that of stationarity, that the translation from NARCAP output to local is preserved into the future. That's what you have to make as an assumption, unless you know otherwise. So then if you combine these, you get this result, which is this last equation. So this is the cumulative distribution function of the predicted precipitation based on current station data, current output, model output, and projected model output. We're using extreme value distributions for precipitation, and we're using the classical extreme value theory here that uses generalized Pareto distributions for exceedances. And this is the equation for the Pareto distribution. It has 2 parameters, shape and scale. And but we fit these to exceedances over a suitably high threshold. The theory requires that this threshold is very, very high. And so for 30 years of daily precipitation, that basically cuts it down to about the order of 200 exceedances. The threshold is typically around an inch or so. Our units are inches, by the way. When you do this downscaling, this final equation has mathematically speaking, has a sort of a complicated shape, but in most cases it resembles very much a generalized Pareto distribution. So there is a simplified version of this downscaling that makes the assumption of same shape parameters for the model outputs as well as for the station pair. There's an issue of threshold selection, and of course you also have to assume a threshold for the projected station data, and this threshold depends on the scales, and so we use this as a standard adjustment for that we used. New England precipitation. So we've done the above procedure. We applied that iteratively for 58 stations and 8 RCM-GCM combinations. So here are the 8 RCM-GCM combinations that we selected. So for impact assessment, so we want location-specific impact, for example, for road and bridges. We want to formulate the impact in terms of extreme events, and this is standard to use return levels, or if you may be familiar with the 100-year flood, or in this case we were calculating 25-year and 50-year return levels. They correspond to 96th and 98th percentile of the extreme value distribution. We did uncertainty quantification by parametric bootstrapping. The downscaling equation can be written in terms of the percentiles, and so once you have that, you can simulate from that percentiles distribution, and so we did that for all 3 fitted distributions as well as then for the downscaled, and from that we derived the downscaled simulated values. That gave us, we then examined 90% bootstrap confidence interval for each station and RCM-GCM combination. So here are some results. So this is the difference between projected and current 25-year return level. So this is the change from current to future, you can think of it. And of the 8 models, I'm only showing 3 just to illustrate the differences. The 8 models, I didn't think they would be visible on the page. So you can see there's quite a bit of a difference between, for example, Canadian models, ERCM, and HRM3, driven by GFDL, and so on. So looks like quite a bit of differences, increases for some models, decreases for others. However, there's quite a bit of variability. People who work in extreme value theory, return levels are highly variable. So the previous slide, sorry, was for only the RCM model. This is now for the local projected. So now we're comparing measured extreme value distribution at stations with projected based on the downscaling methodology. And we can still see some differences. Again, the bubbles are all on the same scale, so large blue means decrease, large red means increase. Next, we were interested in examining the lower 90% confidence bound. So in other words, this is the lower endpoint of the 90% confidence interval. So if that endpoint is above 0, then that would mean we'd have a significant increase based on a 95% confidence interval. And so here, this is for RCM. This is for just the RCM current versus projected. And you can see there's a fairly many locations that have a significant increase. So the RCM actually, the RCMs project a significant increase in precipitation. Now, one thing what happens due to our downscaling method and our uncertainty quantification, which of course adds uncertainty because every time you combine these CDFs, you add a little more uncertainty. And so in the end, when you look at the downscaled projected minus current 25-year return level, confidence bound, now you get very few that are red. And that's just because we ended up with larger confidence intervals. And so the significant increase is very minimal in this case. And so, and that's the reality of, I guess, of uncertainty quantification. And the last thing we did was we wanted to validate our downscaling method. So we did a validation set, chose the first 70% of the observed data as current, as training set, and the last 30 as validation set. And we did a Kolmogorov-Smirnov test of the fitted distribution of the observed minus the ones of the downscaled, and we got this result. So this is the p-values from the Kolmogorov-Smirnov test. So small p-values mean there's a significant difference between the actual observed and the downscale to it, and that would include sort of the there's a question about the validity of the downscaling. So the little points, sorry, this is hard to see, the little points are the small p-values, and so that's where we have, those are some of our problem stations. However, they're relatively few, and so we were really pleased with that result. Conclusions then. So the choice of RCM-CCM combo is it may lead to contradictory conclusions. Significant increase in return level is only at relatively few stations based on the downscaling method. The effect of uncertainty quantifications, again, much fewer significant increases after downscaling. So some works in progress. We also think about weighting the climate model outputs. For example, we want to use the ANOVA design. For example, we could use the p-values from the Kolmogorov-Smirnov test as a suitability index for downscaling and could use that as a weighting that could be used. So then when we want to downscale to a location, we use all the 12 RCM combos, but we still would have to derive a downscaling formula for that, which is actually not trivial. So that's where I stop.
Okay, great, thanks. We're running a bit behind, and that's basically Bill and my's fault. But rather than getting to blame, let's move on to our last speaker, and I hope you'll all hang in to hear Jin-Won Kim speak about model errors in simulating precipitation and radiation fields in the NARCAP hindcast experiment. Take it away.
Okay, this is a collaborative study between 3 institutions that includes UCLA, JPL, NASA, and NCAR. I acknowledge my co-authors for this study. And the background of this study is that precipitation and surface insolation are among the most crucial variables in shaping the energy and surface water cycle, especially the surface climate. These variables directly affect agriculture and many important associated sectors that we are interested in. Thus, estimating model errors and simulating precipitation and insolation are an important concern in climate simulations and their applications. And we are also interested in that the relationship between model errors in these variables may provide clues for the source of model errors and also improving climate model performance in the future. This experiment is based on NARCAP experiment, hindcast results for data for 1984 to 2003, and we examined the model error relationship between model errors in precipitation, cloudiness, and surface insolation. The domain of investigation over the continuous United States, and we are using outputs from 4 RCMs and their ensemble. This is a simple schematic conceptual diagram of how they are related. It's very simple. The incidence solar radiation is partially reflected by clouds, and the remaining comes to as insolation. And the clouds, some of it precipitates, which is contributes to total precipitation. Some is just a non-precipitating cloud. So all told, it is expected that in general, model bias in precipitation and cloudiness are positive. That is, if there is model simulates more clouds, then we will probably get more precipitation. And the other way around, if model simulate overestimates precipitation and cloudiness, we'll underestimate surface insolation. So this simple hypothesis, we try to examine how model performs in simulating. This one, the top 3 shows for annual mean, precipitation and cloudiness and surface insolation in over the United States, and the 2 observational data for cloudiness and insolation comes from series analysis, and precipitation comes from CRU analysis. There are 4 models and the ensemble in the bias from this observation for over the 20-year period. It shows that bias shows pretty well-defined spatial structure. It generally, models tend to overestimate mountainous western United States region and underestimate precipitation in the Gulf Coast and southern Great Plains region. For almost all models show that kind of bias. And for the insolation, models generally overestimate surface insolation, except one exception is Registry M3. And for the cloudiness, models tend to underestimate cloudiness over the United States. One exception is for RCM3. But overall, it is not very clear to relate the kind of expected relationship that is overestimated cloudiness will result in overestimated precipitation and underestimated radiation. It's not well holding here. So we just subtracted model the domain average bias values from this field. That is, we are trying to look at the separate the bias field into 2 components. One is domain average value and the spatial anomalies from it. And this one shows that perturbation spatial anomaly field, it shows that the relationship is pretty well defined in this context. We can see the overestimation in the mountainous western U.S. region for individual models. There are some varying degrees, but the ensemble, if you just look at ensemble, overestimation of precipitation is correlated well with overestimation of cloudiness and also underestimation of surface insolation. And the other way around, for the eastern United States and central United States, precipitation is underestimated. Cloudiness is not quite clear, at least for the Gulf Coast. It shows overestimation. And for the rest of the field, it's underestimation. And for the insolation, shows general overestimation. So except in the Gulf Coast, that expected relationship that underestimated precipitation is positively correlated with underestimated cloudiness, and negatively correlated surface insolation is pretty well established here. To summarize, we put into the scatter diagram, and it shows that just for the spatial anomaly and for every season and for the annual mean, it shows that that expected relationship, positive correlation between precipitation anomaly and cloudiness anomaly holds for every season and for every model. And the negative correlation between precipitation bias and insolation bias holds for every season. So at the perturbation level, this one is pretty well established. And this table shows the relationship between domain mean biases in precipitation, cloudiness, and insolation. It shows that the kind of expected relationship between model bias, that is overestimation of precipitation, will relate you to overestimate cloudiness and underestimate insolation, are not well established when you look at the domain average bias values. But if we look at the spatial correlation coefficient for the spatial anomalies, that relation pretty well hold for every season, every model, and even for annual means. So it means that it still is some interpretation, but the models have their own mind in when you calculate the mean precipitation and precipitation, cloudiness, and radiation. But when you look at the spatial variability, they have the right kind of sensitivity to the. So if model underestimates cloudiness, then it will result in underestimation of precipitation and overestimate cloudiness. That kind of spatial variability is well established. So this is a kind of two-phased performance in model. Models does not show the kind of expected scale in simulating the bias relationship in domain average values. But when we looked at the spatial variability, that is your sensitivity, that turns out to be correct. And I'm still trying to digest this and try to interpret. But this is one result we may look at further, and perhaps related with, we may be related with model scale in general. Thank you for listening.
Okay, well, we do have time for a couple of questions. Of course, it's really impossible to see anybody out there. Adam?
This may be saying the same thing that you just conveyed, but I'm just wondering, with your analysis, if I understand the NARCAP data that's provided well enough, I'm just curious about what the non-precipitating conditions are. In other words, you're seeing this situation where, yeah, you are seeing some consistency between precip, cloudiness, and insolation errors. What happens during the non-precipitating conditions? And maybe this is something that's sort of clouding clouding your analysis.
Yeah, the possibility is that, in reality, we have overcast days, or we don't see any precipitation. So that happens in the real world.
Right.
In that case, we expect the precipitation cloudiness will not be closely correlated. but cloudiness and surface insolation will be related. And I had to skip some things to shorten this talk, but the key is that one of the keys that the cloud relative property is not determined solely by cloudiness. It includes cloud type and especially the mass content, size distribution, and phase of cloud particles. So what I did here is the very simple-minded, the everyday kind of climate variables we can have in our hand and try to examine it. But if we are going to dig further deep into the physical processes, we will have to look at additional variables that are directly related to cloud properties.
All right, okay, thanks very much, Jaewon Kim.
Thank you for listening.
And thank you all for hanging into this, the very last, and thanks for attending our session, and thanks very much for all our speakers and all the great research they've done with the NARCAP dataset. Have a great evening.